Now I want to start talking about time independent. So time independent and for this I need to introduce something called stationary states. So let's think about this. So we need to solve Schrödinger equation to obtain psi as a function of position and t. And for the moment I'm trying to make it simple, and there's only one dimension and one time. And we need to find given the only unknown in the Schrödinger equation is v of x comma t. So this is the external potential. And now, which is generally the case, if you look at nature, we generally have time-independent potential, right? For example, this room is kind of like a box and the walls are not moving. Or if you have like some harmonic oscillator, it has some potential, it's not moving. And we can also assume it from a pragmatic point of view because it's going to simplify things and help us understand a lot of things. So what I will assume is Vx comma t is V of x and no time dependence. If this is the case, we try separable solutions. And separable solutions are like, I'll try to be careful with this. Use uppercase psi for full solution, lowercase psi for x dependent part, and var phi, this curly phi, for time dependent part. And the job now is to plug this in Schrödinger equation and see what it gives us. So let's write Schrödinger equation. Can you? So this var phi. So this is like a Greek letter phi, but it is, so normally this is lowercase phi. This is uppercase phi, like kind of like cursive, right? You can write cursive. Like a cursive phi is like this var phi. So this psi del t is equal to minus h bar squared over 2m partial squared partial x squared. This uppercase psi plus v only depends on x, and this is uppercase psi. Now let's plug in. So I'll copy and I'll replace, whenever I see this uppercase psi, I'll put this lowercase psi which only depends on x and var phi which only depends on time. And the same thing here, psi here and var phi, and psi here and var phi. Okay. So I think I told some of you, if you want me to pause so that you can do it on your notebook, let me know. Sometimes I can just forget to wait. Please remind me. Now I look at this side. So this side. So this is like a derivative del t, and this derivative is going to go and find something that depends on t. But psi does not depend on t, so I can just take this psi outside, right? I can just take, maybe I can do it in 2 lines. Maybe let me do it, not to clutter too much. So I will just take this psi and put it outside because the time derivative doesn't know about x. I come here and I look at this, there's like psi and phi, right? This is a derivative in x, but phi is only time dependent, right? Then I can safely just take this guy and take it outside here so that it doesn't know about the derivative. Let me just push it just a little bit. Like in the second step, now when I look at the partial derivatives, there is no need to do partial derivative because this object already only depends on time. So, but if you leave it like partial derivative, that's fine. But to be technically correct, let me just also do that, which actually does not make any difference. And same thing here. And in this second step, I am now going to divide everything by psi times phi. Let's divide it by psi times var phi, divide it by psi times var phi, and divide this entire thing by psi times var phi. So let me copy this entire thing. So cancel this. Cancel phi's. So let me write it like 1 over psi and cancel this. Good. And now let me just write it a little bit nicely. This is d phi dt, and this is d squared psi dx squared. Good. Now, we look at this equation and we say that, okay, the left-hand side, so this side is only t dependent, right? There is nothing other than t. There is no x here. I come here and I look at this side. This is only x dependent. Like t is a variable that changes, x is a variable that changes, but left hand side and right hand side, they keep being equal to each other for all x and for all t. And how can we achieve this, right? There is like some variable and it seems to be equal to something as a function of some other variable. And our suggestion is the only way this can be happening is this side is a constant. And if this side is a constant, because this is an equation, this side is also a constant. Is that good? Constant in the sense it doesn't depend on x and it doesn't depend on t. Good? And the reasonable thing is to call this constant E, which will turn out to be energy in a little bit. And now we have two equations, right? So this entire thing is equal to E, or I can write it like I h bar d psi dt is equal to d var phi is equal to E times var phi, and the same thing here, minus h bar squared over 2m d squared dx squared lowercase psi plus v of x lowercase psi is equal to E psi. Good. So the last part, when we assign constants, so we said this part is only t dependent, this part is only x dependent, and they are always equal to each other. And this can only happen if each side is a constant. Each side is a constant means it's not dependent on x or t. And this constant, you could call it C, but because we are going to do this a lot and it's going to turn out to be energy, we call it E. And the second one is important equation here. So this is time independent Schrödinger equation, or let me call it TISE for short. So in this case, this is like a stupidly simple problem, but this is like a very profound, right? And you may have to do this in also very complicated settings, but the observations are going to be the same. And the what we did here is we had one PDE. We had like a partial differential equation. It was like a first order in time and first order in time, second order in x. by assuming separability, we reduce it to two ordinary differential equations. This is two ODEs. And if you have taken mathematics, you know ODEs are like much simpler than PDEs. Good. And the first one, this one is so simple, we can just solve it in no time, right? If you want, this is 1 over phi d phi. I'll rewrite this equation is equal to minus I e over h bar. Right? I didn't do anything, I just rewrote it. And I don't know how people showed it to you. The way I was taught was you just take this dt to here and you integrate both sides. And here there's only time to integrate. And integral of dt is this. There's nothing simpler than that. This is t plus a constant. And integral of 1 over phi d phi is logarithm log phi. And now this is solved, right? Phi is going to be some constant times e to the minus I e over h bar t. Any questions? You can pause just for a second for you to write or think about the question. So let's consider, okay, the full solution now is going to be, I'll absorb this constant in the normalization, like this is full solution is psi x comma t is going to be this constant inside this lowercase psi times e to the minus I e over h bar t. So this is what we call a separable solution. And let's observe some properties of separable solutions. First, if you calculate the probability density by taking the absolute value square, you immediately find this psi of x. Let me write it in two steps. This is right psi star psi, and for calculating psi star, I need to have this factor and its complex conjugate, and complex conjugate of this is going to be plus e to the I plus times e to the I minus. They just cancel, and you at the end have, okay, there is also square here, psi x squared. So this, the nice thing about this is like this is time independent. Similarly, if you calculate any observable, like let's use Q for like undefined observable, which may be a function of x or p, which doesn't matter for us. And the way we calculate these things are like we put psi x comma t with complex conjugate here, we put q x p here, and we put psi x comma t here. And the same thing, right? There is, because of complex conjugation, there will be e to the minus I over h bar et, but whenever I take the complex conjugate, this is going to be plus, and this one is going to have e to the minus I over h bar et. Plus minus, they cancel each other. All the time dependence is cancelled, and at the end this is time independent. So I first wrote the dictionary for us, right? The way we calculate expectation value is you write the integral, you write psi star, which is a function of x and t, you write whatever your interest is. I left it unspecified, and you put psi. The important thing is this one is psi star, this one is psi. That's the prescription we'll have to follow. Because of that, this e to the I is cancelled and time just dropped out. So that's why we call these separable solutions stationary states. Over time, we'll understand that they are like very important. They have very special properties, and non-stationary states are also going to have very important place in our understanding, like radiations and transition things like that. But for now, forget what I just said. So the second property. So let's consider the expectation value of Hamiltonian. So I can consider Hamiltonian to be an operator, h bar squared over 2m d squared dx squared plus v of x. I may also at some point stop writing v of x because almost all the potentials we use are going to be time independent. And the Schrödinger equation, I like writing in operator form because it's faster to write and easier to make calculations like this. So this is also time independent Schrödinger equation. And now so this is what I call operator. Operator means it's telling you what to do, and you do it, and that's the function of this entire definition. Now I want to calculate expectation value of Hamiltonian, and our prescription is exactly the same. Write dx, write psi x comma t star, write the operator you are interested in, and write psi x comma t. And since time is dropping over and over again, maybe I can just like speed it up and skip that step. You can simply just write this lowercase psi, and this is lowercase psi. There is no time anymore because cancellation is always like that for separable states. And now I look at this side, h times psi. I know what this is equal to. This is like e times psi. But e times psi, right? E is a constant, independent of x. That's how we started the whole thing. Then I can take this e outside. But we said we want normalizable solutions. And even if the solution is not normalized, we can normalize it by hand. That means this integral is going to be 1, and this whole thing is going to be equal to e. Okay? And I can repeat the calculation with h square. And the logic is exactly the same. So this is h times h, if you want, h square. I apply 1s first. This is e times psi. And e is a constant, take it outside. There's one more h, act one more time, it's going to be e squared. And again, what remains is normalized. So this is going to be e squared. Now I can calculate the variance. Sigma of h squared is by definition h squared minus expectation of h squared, and this is e squared minus e squared, and this is 0. So this is 0 variance. And the interpretation of this result, if you have separable states, any separable state, if you make the measurement of energy, measurement is exact, right? Because there's no variance, you get exact measurements. And this like a special case valid for separable or stationary solutions.
When it's not dependent on time.
Yeah, exactly. Because this calculation says that. Any questions? Yes.
In order for us not have zero variance, then does our function have to be
Yes, yes, exactly. If you have like a time-dependent solution, it's going to have variance in energy. Or another way to say it, the energy will not be well defined. Yeah, there will be some uncertainty in energy. There will be some spreading in energy, but that's not the case for stationary states. Okay, so this is number 2. Number 3, suppose you have one separable solution, psi 1, x comma t. There is like some x part, and there is some corresponding energy minus I over h bar. Let me call this E1 times t. So we now know this is a solution with corresponding energy E1. And I can take another solution like this. So suppose this is like a solution psi 2 corresponding to lowercase psi 2. And let's say the energy for this case is E2. And by linearity, right? Schrödinger equation is linear. Any other combination like this, psi 1 x comma t plus b psi 1 x comma t is also a solution. In fact, if we have like many solutions, right, we can write so 2, thank you. That's 2, yes. Like any solution, in fact, can be written like this. And okay, if you choose Cn properly by suitable Cn set. So for the moment, I don't show you this, but hopefully in the second hour, I'll show you why this is the case with explicit calculation. But for the moment, that's what it is. But the important thing about this kind of solution, okay, let me say this, and then I'll give a break. I think that's the last point, I think. Okay, that's the last point, and then I'll take a break after that. But the important thing about this kind of solution, let me call this this psi of x comma t without any subscript. And let's look at the observables, like for example, probability density. Probability density is psi absolute value x comma t squared. And to calculate that, I just need to take this and multiply it with complex conjugate. And for simplicity, let's assume A and B are real. We can also take them to be complex. Let's shorten the calculation just a little bit. So this one and this one, and times without complex conjugate. So assuming A and B are real. And what I need to do is like here, there is like e to the minus I over h bar E1 times t. And because of complex conjugation, I need to make it this plus. And I need to do the same thing here. So this is now E2. And so here, this one has minus, and this one is E1. And the same thing here. And this is E2. Good. So I'll just multiply term by term and see what it gives me, and then I'll try to make an interpretation, and that's the end of this lecture. So A times A squared, and because there is like psi1 inside, this is, and also let's assume psi1 is real, it doesn't matter, psi1 squared x, this is e to the I, e to the minus I, and there is no time here, plus A times B, psi1 times psi2, and now I have e to the I over h bar, e1 minus e2 times t, right? There's plus e1, there's minus e1, and I have this there. Plus, now this term times this term, AB is equal to BA, AB. So this is again psi1 and psi2, and this is e to the, now I want to write it like this, minus I over h bar. The minus term is e1 minus e2 times t. And lastly, this term is going to cancel this term, and I'm going to have b squared psi2 squared. And at the end, I have this a squared psi1 squared plus b squared psi2 squared plus this term, and this term I can combine to give 2ab psi1 psi2 cosine e1 minus e2 divided by h bar times t. Therefore, probability is time dependent, and it actually oscillates with frequency. Let's define it to be omega e1 minus e2 divided by h bar. And if you calculate any other physical quantity, they are also going to be time dependent. So just to finish, we started two separable solutions, right? We used linearity to write a solution, right? This is also a solution of Schrödinger equation. But if E1 is not equal to E2, resulting probability distribution or probability density and resulting expectation values are going to be time dependent. For the moment, this is just an observation, but later this will also be important. Any questions or comments? Maybe we can take a 10-minute break and continue.